thanks everyone for coming here to the ODSC meetup. We just had, for those of you who already know, the ODSC East West meetup that just came in last week. We had 4,500 people. It was a huge turnout of everyone from data scientists to researchers to executives, all over the board, everything. And really, it was such a great event. SAS is actually one of our partners. So actually, thanks so much for SAS for helping us out. So here we have Tyler, who's a systems engineer at SAS, who's going to be talking about deep learning in real time. So Tyler, let's introduce Tyler.
Thank you. Hey everybody, let me know if you can't hear me okay or anything like that. And please remind me to repeat questions for everybody so that we can all hear. Like Jonathan introduced, my name is Tyler Freckmann. I work at SAS as a systems engineer. So my job is to support all of SAS's customers and potential customers in everything across the data analytics lifecycle. So I work with data management products, data visualization products, statistics, machine learning, all sorts of different types of advanced analytics, as well as operationalizing those analytics into actual production environments. So that being said, I'm going to say straight off the bat, I am not an expert in deep learning. My presentation is going to be a little bit more of an introduction. I'm going to show you how SAS does deep learning. You'll see some of our packages that we've released and everything like that. And I'm also going to show you how to deploy deep learning models in real time. I think that I am actually going to start with that at the beginning so you can really get to the meat of it. And those are actually the products that I work with most. I work with integrating our APIs into third-party systems, event stream processing, things like that. So, I will not be offended if you choose to leave because this is, too low level for you. I know we all have busy lives, but without further ado, I'll get started. So, unfortunately, our my computer has to be over here because I don't have a clicker and there's no way to move it up here. But I'm going to actually start off first with a demo. So,
I can help.
Oh, I'm going to do a demo, so I need to be on the computer. Yeah. So I'm just going to hang out right here. And can you hear me okay if I just talk like this? That's good. All right, I'm just going to turn this off for now. Okay, so what we have here is SAS event stream processing, which is a product. There we go. Which is a product that we have for real-time complex event processing. It's what it sounds like. This is a project that we have, and if I open up this project, here we go. Yep. Is that better here? Yeah. All right. So the basic idea behind this product is it's a extremely fast, high throughput event processing engine that can be deployed in resource-constrained environments like routers and gateways and things like that, or on a production-grade server if you're processing gigabytes of data at a time and you need all of those resources and everything like that. But the general way that you work with this engine is you define windows that do units of operation on your events. And this engine is designed for all sorts of different types of stream processing. If we look at, it could be transactional data, unstructured data such as blobs, which is what I'll be showing you, but it could be standard transactions and things like that. And you have all sorts of transformations and analytics that you can do on your events, as you can see examples of here, other like pattern detection, geofencing, text analytics, like content categorization, sentiment analysis. So it's pretty robust. Basically everything, all the different types of analytics that SAS does get ported over to the stream processing engine for real-time actions. But what I'm showing you is an example of how to do real-time image classification using the engine. And so we have a couple of windows here to do the processing. And the first window is where we take in our images of our source window, and then we resize the images to fit into the convolutional neural network model that we have to do the image classification. And then finally, we have our score window, which is where the scoring actually takes place. And on the other side, this is where we actually send in our models. So once you have the engine running, you can switch out whichever model you want to use on the fly by just sending a new model. And that's this side of the flow. So I'm just going to go ahead and start this test here. All right. And the reason I'm starting with this is because I kind of want to show you the end product and what's most exciting first of all, and then we can go through the gory details later. But now the engine's running, no events are streaming through yet. But the next thing that I want to do is actually connect to a real-time dashboard so you can see the results streaming through as well. I'm sorry? It can be. So you can deploy it pretty much anywhere, in Docker containers or on Bear OS in your own environment. And you'll have to forgive some of the latency because this is across a VPN. Okay, so this is the stream viewer. And like I said, there's nothing going through the engine right now, but I'm just going to start publishing some images. And we have a publish and subscribe API in Python, Java, C++. So you can connect to pretty much anything you want. We also have out-of-the-box adapters for all sorts of like the OSI, PySoft system or Kafka. So it's designed to connect to really anything, but I'm just using a Python API to just publish some images here. So I'm going to connect to, actually, yeah, I'm going to connect to this server. CESX 15043. Okay, and then I'm going to tell it which model I want to deploy, which is that convolutional neural network model. Oh, I need to give it a fully qualified path name. All right, and I'm just telling it where to find the images that I'm going to be publishing here. All right. So it is now publishing the images, and I think I just need to refresh this once more. And we should be seeing some images start to populate here. This is our testing facility. And let me make sure that I'm not getting any errors here. Yeah, looks like it should be okay. Sometimes it takes a while for, there we go. All right, so I'm getting some images in there. All right, here we go. So now it's classifying the defects of these images in real time. So on the left-hand side, you can see the image, the label of the defect, and this is actually with one of our partners, a high-tech manufacturer that builds hard disks, and they want to do basically like error detection on their images in real time. So this is the picture of basically the different types of errors. So for us, it's hard to kind of tell like what the different classes are that the model is classifying. But on the right, you can see the predicted probabilities for each of the different classes on each of those images. So the way that we built this was basically we used SAS's deep learning toolkit to build our convolutional neural network model. We took the model, threw it in, which ends up being just a binary file representation of the model, threw it in the real-time streaming engine flow that I showed earlier, and we're up and running with our classifications. So that's One of the reasons why, there's tons of options out there, TensorFlow, Keras, PyTorch, 1.5 million different things, right? Caffe. I'll speak to how our deep learning toolkit can integrate with those things as well. But one of the questions that SAS frequently gets is, well, why would we want to use a deep learning tool that you guys have when there's so many open source options available? And one of the big reasons is that we can deliver these types of additional capabilities like the real-time processing, the real-time dashboarding, and that kind of stuff as well. All right, so I'm going to jump back into the PowerPoint here and get started. Oh, so like I mentioned, we don't have, this is the best that we can do here, and I have to click through the slides here. So I'll just be hanging out here for the rest of the presentation. All right, so regarding deep learning, I feel like anybody who's heard of deep learning has heard 1.5 million acronyms and words regarding that topic, autoencoders, a million different types of like convolutional neural networks that I was just talking about, LSTM, ReLU, ResNet, like what are all these things, right? So I'm hoping to clarify some of that for anybody who's not familiar. And if you are an expert in deep learning who's here, feel free to interject. It's a meetup, right? We can be kind of collaborative. So yeah, I welcome any questions, comments, anything at all for sure. Okay, so a little bit about the evolution of deep learning. So neural networks were actually first published in the 1950s, and that's when the term artificial intelligence really kind of started to circulate in the literature a little bit, but it took until pretty much now for it to be on billboards on the 101, right? And so in the 90s, we started to see a lot more like actionable machine learning, for different kinds of classifiers in serving ads or predicting defaults, fraud detection, different things like that, right? And so, you have your decision trees and different things like that. But currently, deep learning is the biggest craze. And a major reason for that is the algorithms have been around for a while. The algorithms are improving, but I feel like a much bigger reason for that is there's so much more data available that you can actually use to make your decisions, as well as the compute power necessary. So most deep learning takes place on GPUs because it's so computationally intensive. It takes a long time for the algorithms to run through the numbers with the amount of data that's required to actually get a good model. And so now that you have general purpose GPUs available to run this, it's just exploding. And that's one of the things that our deep learning toolkit can run on GPUs as well as CPUs. And most of the other tools like TensorFlow and Caffe and those different products can run on GPUs as well. And that's all leading to this actual, like, let's not just have a deep learning model in our paper that we're presenting in research, but let's actually do something with it online. And one of the things that I just learned about at the Open Source Data Science Conference was this new idea of generators. And a colleague showed me a video of Barack Obama speaking in a place he had never spoken before and saying things that he had never said before. And this was like a high-res video. And that video was created from a deep learning model generator. So the idea of being able to actually create high-res video of something that's never happened before is a little bit scary as far as artificial intelligence goes, but there are people working on other methods to determine if what you're seeing is from a generator or whether it's from real life. So it's a really exciting time we're living in. All right, so backing up a little bit to different types of machine learning methods, supervised learning methods is where you already have labeled data. You already know what the different classes are. You already know what you want. So if you're working on a spam classifier, you already have emails that represent spam and emails that don't represent spam. in my example with my customer, we already had pictures that represented the defects and pictures that represented normal behavior. So that's supervised learning. Unsupervised learning is where you just have data. You don't know what's in the data, right? So one of the most classic examples of this is clustering, where you have a data set, and then using the k-means clustering algorithm, you can determine which groups of data points are similar to each other. And then once you have those similarities, you can start to market to those distinct groups, or you can use those similarities as input to some sort of predictive model as another feature or something like that. Semi-supervised learning is where you have a combination. A very common example is autoencoders, where the job of the model is to basically create a map of the inputs by creating new features. And reinforcement learning is where you're basically trying to train an agent using some sort of reward mechanism on good behavior. So it's kind of similar to supervised learning, in which case you know what you want to happen, but it uses different methods. It's very popular in robotics for training, a robot how to walk or something like that. You don't train a robot how to walk by giving it a bunch of data points saying like this movement is equal to walking. Instead, you just say, if you try a movement that is going to get you in the right direction, you're going to get a reward, and then the algorithm incentivizes those rewards and tries those behaviors over and over again. Okay, so I'm going to jump into a little bit of a refresher about what neural networks even are, how they work, because neural networks are really the core of deep learning. So let me move into that. Where is it? Here we go. So this is playground.tensorflow.org. And I'll make this a little bit bigger as well. I'm going to keep doing that. Okay. All right. So what we have here is two classes, right? We have our blue is spam emails and orange is non-spam emails, or something else like that, like defects and non-defects. And we're trying to create a model to predict which is which. And using standard machine learning methods like regressions, where you have, two inputs, right, an X and a Y, you can train the model to fit a group like this, right? So this is kind of a representation of a logistic regression where we have two classes and we create a line in between them using a combination of the two inputs. But frequently our data is not exactly into these two clumps like this, right? So we might have something that looks like this. And if we try to just train on those two inputs, X and Y, it's not really going to work out. And so traditional machine learning would be, okay, I'm going to explore my data. I'm going to see if I can visualize it. And when I visualize it, I see that it kind of develops this pattern. And so maybe I want to try adding the product, right? That's a new feature that I'm going to manually create here. And so once I manually create that feature, I'm able to fit the model much better. Same thing goes as if I, have a circle and I'm like, okay, I know that circles have to do with the squares of my inputs. And so I'm going to create those features, and I'm manually creating the features, and I can create my model much better. But frequently we don't just have two features in our data, right? We don't just have two variables. We have 300 or something like that. And being able to visualize the data in order to get